Hello, my name is Steve Miller. I'm a math professor at Williams College. I'm here with my assistant, Cam, and the goal today is to talk about from Pascal to calculus. So what we're going to do is we're going to start with just some concepts from Algebra 1, and we're going to see if we can actually get to calculus, and in particular to some of the wonderful applications of calculus. And so this is probably going to take more than one day to go through it all. So when we're done, we will not only see stuff about Pascal's Triangle, which is the first part of the talk, but we'll also see some stuff about solving equations. We'll see some stuff on chaos and some stuff on fractals. So the first is Pascal's Triangle, which people may or may not have seen. So what will we be using all of this for? Why do we care about Pascal's Triangle? Well, there's a lot of great properties hidden in the numbers, but it's going to help us as we go from algebra to one of the two main parts of calculus, differentiation. So what is differentiation? What is calculus? Well, differentiation is all about how functions change. So we might have a function that represents our distance from home. And as we talk about how that changes, what quantity might that represent?
Like, what do you mean?
So if you look at how distance changes, what quantity would that be? It would be...
Like, for distance? Like, what do you mean?
Well, if you look at the rate at which distance changes, that might
either
be...
like positive?
Well, what might you... What word would you use for that? This is the object's what?
Speed.
Object speed. So speed is the rate of change of distance. And that's one of the big things we're going to look for. And so we're going to find some wonderful applications of this, which is going to lead to chaos and fractals. Okay, so Pascal's triangle, what is this? So the way Pascal's triangle works is you have two diagonals of ones, and then the numbers inside each one is the sum of the number above and to the left and above and to the right. So 2 is 1 plus 1, 6 is 3 plus 3, 5 is 1 plus 4, 35 is 20 plus 15. There's a lot of different ways to interpret where these numbers come from. So once I give you this rule, if I give you the line 1, 3, 3, 1, the next one has to be a 1 and a 1 on the outside, and then 4 would be 1 plus 3, 6 would be 3 plus 3, 4 would be 3 plus 1, and then you would just have the 1. So as I mentioned, there are lots of different ways of finding where these come from, giving rules for them. For us, because we want to get to calculus, the most important is if I give you this quantity x plus y and I raise it to the nth power and expand, these numbers are going to come from expanding x plus y to the n. So let's just review how you expand things. So the big word that people often use is FOIL. It stands for first, outside, inside, last. And it allows us to multiply expressions like a plus b and c plus d. So we have a plus b and c plus d. What would the first be?
AC.
A times c, that's what we have over here. And then the outside would be the a and the d. The inside would be the b and the c. And the last would be the b and the d. So if you look at it, we can write this as a times c plus d plus b times c plus d. So there's going to be 4 terms, and FOIL is just a way to make sure you don't forget which goes where. So here's a couple of things to check. 3 plus 5 times 7 minus 2. So how would you compute 3 plus 5 times 7 minus 2?
So that's really 8 times 5.
Yeah, it's 8 times 5, which is?
I don't know.
40. So we could actually compute it easily. But we could also do 4. It would be 3 times 7. That would be 3 times negative 2. Then 5 times 7. And then 5 times negative 2. So 21 minus 6 plus 35 minus 10, which does equal 40. Now here's 2 more useful ones. Have you seen this one before? X plus y times x minus y.
Yeah, I think. Well, we just did that, sort of.
Well, yeah, and this is just letting a and c be x and b.
I mean, you could look at it like x plus y times x plus a negative y. Like,
and then x plus y times negative y.
Yeah.
So the first is going to be x times x.
Yeah.
The outside is x times negative y. The inside is y times x. And the last is y times y. What happens to the 2 middle terms?
Wait, is it y times? Is that y times?
I'm sorry, y times negative y. Thank you. Y times negative y. So we have x squared minus xy plus yx. Well, what's true about minus xy plus yx?
They cancel.
They cancel because it doesn't matter the order in which you multiply.
X squared minus y
So it's
squared.
x squared minus y squared. And as a check, if I gave you 4 minus 2, I'm sorry, 4 plus 2 times 4 minus 2, that says it's the same as 16 minus 4.
Yeah.
And then you could do, instead of x plus y times x minus y, x plus y times x plus y. And now it's the same except you don't have the minus signs. And now, rather than cancel,
you just add it.
you would just add it. It would reinforce and you get 2xy.
I've seen that before.
So this is extremely useful. So we can.
Wait, how did you get the y squared?
For which one? For the last one?
Yeah.
Well, that's from the last.
No, from the top. From the middle one.
In the middle one? Y times negative y will give you negative y squared.
Oh, yeah. That is, okay.
Yep.
Yeah.
So we just did x plus y squared, and when the dust settled, it was x squared plus 2xy plus y squared. If we want to calculate x plus y cubed, mathematicians are lazy. We like to reduce things to things we already know. Well, x plus y cubed, that's the same as x plus y times x plus y squared. Do we know what x plus y squared is?
Yeah.
Yeah, it's just right over here. So now what we do is we say it's the same as x times this whole thing plus y times this whole thing. And that's why the first term here is x times the x plus y squared and the y times x plus y squared. Now what's x times x squared?
What's x cubed?
X cubed. And then x times 2xy is?
3x squared y.
It's x times 2xy.
Oh, so never mind. It would just be 2x squared xy.
Just 2x squared y.
Yeah.
We had 2xy. We multiplied by another x. Now we have 2x squared y.
Yeah.
Now we multiply x by y squared. What do we get?
X times x. Yeah, it would be xy squared.
Xy squared. And now for this side, we have y times x squared, which is?
It's like the same thing, just like reverse. So
Yeah.
you get the 3x squared y.
Well, let's do it slowly. So y times x squared is?
Yx squared.
Right, and we normally write the x term first and then the y term second.
Yeah.
So I'll write it as x squared y. And you have y times 2xy. What would that be?
2xy squared.
And there's the 2xy squared. We had 2xy, and this increases the power of y by 1. And then the last one is y times y squared is?
Y cubed.
And now we just add. So we have an x cubed, we have a 2x squared y, and we have an x squared y over here. So how many x squared y's do we have? There's the 3x squared y. Similarly, we get 3xy squared and y cubed. Could you compute x plus y to the 4th?
Yeah.
Yeah, you would just take x plus y cubed and multiply that by x plus y. So if you're looking for a good homework problem, if you're listening, calculate x plus y to the 4th. Calculate x plus y to the 5th. Now, the only difference between this slide and over here is I'm putting in red the coefficients. 1, 3, 3, 1, 1, 2, 1. Do those numbers look familiar?
Yes.
Where have we seen them?
Pascal.
Yes, we go back to Pascal's triangle. 1, 2, 1, 1, 3, 3, 1. We said that they were the coefficients from expanding. So this would actually, if you want to calculate x plus y to the 4th, it's just going to be x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. As you go down, the power of x decreases by 1 and the power of y goes up. This is one of the reasons why we love Pascal's triangle. It helps us compute this stuff quickly. Now, we did x plus y squared and x plus y cubed. We could have also done x plus y to the 1st, which is pretty easy. It's just x plus y or 1x plus 1y. And you can see the Pascal triangle.
And if you do it to the 0.
And so if you do it to the 0, well, what should anything to the 0 be?
1.
It should just be 1. So as long as you don't do anything silly, like infinity to the 0, or
like,
0 to the 0.
Yeah. Like 0 plus infinity
Right.
to the 0th power, that's going to cause some
So
trouble.
we should extend it to 1. And here's the beginning of Pascal's triangle. And so we can keep getting more and more rows as we keep going further and further down. And so why is the Pascal relation true? So each number, as I said, is the sum of the number immediately above to the right and to the left. So 4 was 1 plus 3, 15 is 10 plus 5. Why is this true? So I'm going to just sketch the proof. We're not going to prove it rigorously, but let's assume we know the 5th row of Pascal's triangle. So let's assume we know what x plus y to the 5th is. Okay?
Mhm.
And so we do the work, we see it's x to the 5th plus 5x to the 4th y plus 10x cubed y squared and so on.
Mm.
If you want to calculate x plus y to the 6th, it's just x plus y times x plus y to the 5th.
Yeah.
That's the same as x times x plus y to the 5th plus y times x plus y to the 5th.
Yeah.
And where do we know what x plus y to the 5th is?
Yeah.
It's all the way up here at the top. So
That's gonna be fun to do.
so we
Do we
plug
have
this in.
to? Are
Well,
we gonna go over that?
We're going to go very quickly. What's x times x to the 5th?
X to the 6.
What's x times 5x to the 4th y?
The same thing, just 5x to the 5th. Y.
Y. What's x times 10x cubed y squared?
10x to the 4y squared.
Yeah, so all that this does is it increases the power of x by 1 everywhere.
And then same thing for the y.
And then the same thing over here increases all the powers of y. And now, do you see this very long line that we have to add? On the next line, what I did is I arranged them. So I first wrote this one over here, and then I wrote the second one underneath it, and I aligned them so that the terms with the same powers of x and y are in the same spot. Now it's kind of easy to add. I notice we have 1 over here, the coefficient of x to the 6th. We have 5 plus 1, 10 plus 5, 10 plus 10, 5 plus 10, 1 plus 5, and 1. And there's where Pascal's triangle is coming from. So hopefully this gives you a sense of why Pascal is true. So we can prove many properties of Pascal's triangle. You have a small n, we can expand directly. And then this is what I know I've shown you in the past, but since we're going to talk about chaos later in fractals, I thought I would just quickly show now. So
are you going to show the video?
I'll show the video.
I like the video.
I like the video too. So if we have Pascal's triangle, we're going to modify it. And everywhere we have an odd number, we'll put a dot. Everywhere we have an even, we're going to make it a blank. So initially, we would just have 1 dot. Then for 2 rows, it would be dot, dot, dot. For 3 rows, it would be dot, 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 blank, dot, dot. 4 rows, dot, 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 dot. It would be a triangle with something missing. And so here's the 4 rows. Here's 8 rows. And then what I did is I wrote a program, and I was surprised that no one else seemed to have written a program to do this. So rather than having the triangle at the top going down, it was easier for me to have the triangle starting at the origin and expanding out, going eastward, going in the x direction. And what I'm doing is, as you keep going out, I'm adding more and more rows. Well, I don't have a screen that's infinitely big, so if I keep adding more and more rows, it's going to go off the screen. So I'm constantly renormalizing so it always stays in the same box. And you can see a beautiful fractal structure emerge.
Oh, this is a fractal.
This is a fractal. So what I'm going to do now is I'm going to stop the share. I'm going to go to the video here. Okay.
It's on mute.
It is, right, I just put it on mute.
Why?
Well, because I'm talking right now, so I don't need to hear the recorded Steve talk. We can have the actual Steve talk.
It's like, should it be on mute?
No, because I wanted to just jump to some part in the middle. And so for those of you who are making videos, it sometimes has issues if you record with audio coming from. So here is your Pascal's triangle, and here's showing, for instance, some of the numbers. And so now I'm going to run the video, and I'm going to show what happens as we add more and more rows. So in a moment or two, you're going to start seeing the dots.
Oh, no.
We have, unfortunately, a slow internet connection. This is due to the coronavirus, and everybody in America now stuck in their houses and all using the same slow internet connections in good places. And so if you look, it almost looks like a superstar destroyer from the start of a Star Wars movie. As you add more and more rows, you can see the same structure. And so the video, Steve, is circling this part here and saying it's the same as this part here and that part there. And then this whole thing here is the same as this part here and that part there.
I wish it was unmuted. Let's hear the words of wisdom.
No, because the audio will not work well if the voice is coming from the computer. It's an interesting question as to how would you actually write a program to do this. I didn't write the most efficient one, but that would be another wonderful lecture to talk about how you do all of this. So I'm going to stop the share. And what I'm going to do is go back now and go back to the slides, which I think right here. Okay. So now we're going to go to part 2, algebra and limits. Have you done any limits in anything you've done in class
I
yet?
don't think so.
Okay, so we're going to do some new concepts. So the first we're going to do is evaluating functions. So what is a function? So,
Like f of x.
so f of x, so a function, can you give me an
Like
example of a
y,
function?
or like f of x equals 5.
So,
5 plus 6 or whatever. I don't know.
well, f of
I
x,
mean, it would normally be something like f of x equals like 5x plus 6 or something.
right, so normally the function,
That's like a slope intercept one.
right, so if you had something like f of x equals 5, it'd be no matter what input you have, the output is always 5. We call this the constant function, and we actually understand everything about the constant function. It's not that exciting. F of x equals 5x plus 6 is more exciting. Different values of x now give you different outputs. But a function will take an input and give us an output. We often use the letter f to denote function. Any idea why we use f? We use f because of the word?
F for you?
No, come on.
Why?
We're recording, come on. What do we use
function?
for function? So you want names that are well associated. So a linear function is a function of the form f of x is ax plus b, where a and b are constant. So this is what you mentioned a moment ago. So here would be an example. F of x is 3x minus 5, or f of x is 7x plus 2, or f of x is 4x plus 17.
Curiosity, for
Yep.
the linear function, why didn't you do mx plus b? Because that would be.
So you could do mx plus b.
Because that is like technically what slope intercept.
Yes, and when you do that, m is standing for the slope. I did a because a and b are the first 2 letters of the alphabet, and so I'm defining my constants alphabetically, a, b, c. But this is a good point that different sources will use different notation. Can you give me an example of another linear function?
Like 3x minus 7.
Yeah, 3x minus 7. So all you have to do is just choose a value of a and choose a value of b. It turns out lines are very easy to graph. Lines are very easy to understand. And the whole point of, or one of the main points of calculus is no matter what function someone gives you, you basically say, screw that, I'm going to look at a straight line. Straight lines are better. So let's take the function f of x is 3x minus 5. And let's evaluate it a few different choices of x. So if I put in 0, it's going to be 3 times 0 minus 5 equals minus 5. If I put in 1, it's 3 times 1 minus 5 equals negative 2. If I put in 4, it's 3 times 4 minus 5 is 7. So have you seen stuff like this to evaluate functions?
Yeah.
And so the rule is, you give me an x, I multiply the x by 3 and I subtract 5. And so here's a plot of what it would look like. So you've seen this before.
We did that like a couple weeks.
So it turns out that because of calculus, if you can understand straight lines, you can understand almost any function. You can approximate almost any function with a straight line. So let's consider a more complicated function that does not look like a straight line.
I don't think I've seen those yet.
So, okay, so this is a parabola or a quadratic. And notice now that the highest power of x is degree 2. So you have some constants a, b, and c, and this is why I didn't use m before. I'm always using a as the coefficient of the highest term in x.
Yeah.
So one example might be 2x squared minus 3x plus 4. And you could plot this by just choosing some points. If I take 0, it'd be 2 times 0 squared minus 3 times 0 plus 4 is 4. If I took 3, it'd be 2 times 3 squared minus 3 times 3 plus 4. So 3 squared is 9, 2 times 9 is 18, minus 9 is 9, plus 4 is 13. So
even you get a curve.
And that's how you get the curve. And so I could plot all the different points one at a time, or this is a way to just connect them all at once. So even though you haven't seen this before, are you comfortable in evaluating it?
Sure.
If I asked you to evaluate it at -1, what would it be?
It'd be -1. So it'd be 2 times -1 squared, which would be just be 1. So it'd really be 2 times
2,
1.
right? So this would just be, so the first piece would be 2 when x equals -1.
Yeah.
Then you have -3 times -1, which is?
Really just 3.
So we would have 2 plus b is 5.
Plus is 9.
Right. And if we look at it, here is -1. And if we go up,
Yeah, it's not very good.
oh, but where's -1? This is not -1.
No.
This is -1 is over
Yes.
here. So actually, if you go up here, it
That's
does look pretty good.
reasonable.
It does look reasonable. And it's always nice when you have something to do a test and see, does this look right?
Yeah.
So
It's good
now,
enough.
instead of doing a polynomial of degree 1 or degree 2, we could do more generally degree n. The problem is if we do degree n, we don't know what letter in the alphabet to go to. Now, Dr. Seuss did write a wonderful book On Beyond Z, where he said we don't have enough letters in the alphabet, but even there, that's not enough. He actually did. So I just plotted 3 ones: linear, x, quadratic, x squared, and cubic, x cubed. And I plotted them for 0 to 1.5. If x is really, really large, which do you think grows fastest? X, x squared, or x cubed?
X cubed.
X cubed. So which one of these do you think is x cubed? The top?
The top.
So the top is x cubed. What's the middle?
X squared.
And what's the bottom?
Well, you know the bottom one has to be x because it's a line.
It's line, and there's the line. But here's what's interesting. For values of x that are equal to 1, when x equals 1, they're all the same. Above 1, the cubic is growing fastest. Below 1,
It's here.
the cubic is the smallest.
And the line is the best.
Right. Because which would you rather have, a half or a half squared?
A half.
Yeah. Which would you rather have, a half squared or a half cubed?
A half squared.
A half squared.
That makes sense.
So now we're going to come to limits. Normally, I think you might not get to these until maybe 10th, 11th, 12th grade, depending on where you're going. So it's one of the most important concepts in calculus. It's the idea of a limit. We want to know what happens to the output of a function as the inputs approach a specific value. So if I give you a polynomial like a line, a linear function, a cubic function, a quadratic function, it's pretty easy. Imagine f of x is 3x plus 5. And we want to know what is the limit as x approaches 2. So what do you think happens as x gets closer and closer to 2? What do you think this goes to?
Closer and closer to 2.
As x gets closer and closer to 2, what do you think 3x plus 5 looks like?
A line. Like what do you
Well, what number do you think it's going to? As x gets closer and closer to 2, what does 3x plus 5 go to? As x gets very close to 2.
2?
Why 2?
Because isn't that what it's going to?
That's what x is going to.
Oh.
I'm now looking at 3 times x plus 5.
Oh.
If x is very close to 2,
Then
what should 3 times x plus 5 be close? It should be close to 11.
like, yeah, that
Right.
makes more sense.
And so it should really just be f of 2, right?
Yeah.
3 times 2 plus 5, or 11, right? Here's another way of writing what we did. What does it mean for x to approach 2? Well, we can write x as 2 plus h, and we can let h go to 0.
Yeah.
So if we want to take the limit as x goes to 2 of f of x, that's the same as the limit as h goes to 0 of f of 2 plus h.
Yeah.
And now if we look at this, we have 3x plus 5. What do we get when we take our function? Our rule is f of input is 3 times input plus 5. Okay?
Yeah.
The input is now 2 plus h. What is f of 2 plus h going to be?
2.
Well, the rule is f of input is 3 times input plus 5. Input is, what if I gave you f of...
Oh, well then it'd be 3 times 2 plus h.
Yep.
Plus 5.
Great. What would f of 1 be? It would be...
8.
But it would be 3 times 1 plus 5.
Yeah.
What would f of 7 be?
3 times 7 plus 5.
What would f of smiley face be?
3 times smiley face times plus 5.
What would f of Yankee suck be?
True.
True. It would also be 3 times Yankee suck plus 5. So you just take the input and plug it in over here. And so when we put in 2 plus h, we get 3 times 2 plus h plus 5. So we distribute it into 3. 3 times 2 is 6. 3 times h is 3h plus 5. Now we want to calculate what is the limit as h goes to 0 of 6 plus 3h plus 5.
What?
Okay?
Yeah.
So I claim the limit of a sum is the sum of the limit. What is, as h goes to 0, what does the 6 go to?
0? What?
As h goes to 0, what does 6 go to?
6?
6. This is the constant function we were talking about earlier. You gave me earlier the function f of x equals 5.
Oh,
No matter what
yeah.
input you give me, I always give you back 5.
Yeah.
So no matter what value of h I give you, this is always 6. So what happens as h goes to 0? What does this stay as?
6.
And what about 3 times h? What would that go to as h goes to 0?
6.
As h goes to 0,
3.
3 times h.
0 then.
Yeah. And what about 5? What would that go to?
5.
5. So 6 plus 3h plus 5
It's really just 11.
is really just 11. It's 6 plus 0 plus 5 or 11. So this is a big concept. Is how does this seem?
What do you mean?
You know, that if I want to calculate the limit of something like this, well, any term that has an h, as h goes to 0, is just going to go to 0, and then the constants, I just add them at the end.
Yeah, that's sort of like finding your y-intercept.
Yeah, it's not too bad. So when you compute a limit, we say the limit as x approaches 2. We can write it x as 2 plus h. The way you should think of this is h is a very small number, but that number is not 0. We are talking about the limit as h approaches 0. It is not 0. It's just getting smaller and smaller. 1/10, 100, 1,000, 1 million, 1 billion. So here's an interesting limit. Take the limit as x goes to 2 of x squared minus 4 over x minus 2. What does the top look like as x goes to 2?
4, 0.
Yeah, it looks like 4 minus 4 is 0. What does the bottom look like?
0.
0. Can we divide by 0?
No.
So we are not allowed to divide by 0. But remember, this is the limit as x goes to 2. X is never equal to 2. It's just getting closer and closer to 2. Or we can write it as 2 plus h with h going to 0, but it's not 0.
So it'd be like around 0.
So it'd be around 0. So we can write this. If we replace x going to 2 with x is now 2 plus h, what would this look like if x is 2 plus h?
A little bit greater. Well, that'd really just be h, the top, right?
Well, what's 2 plus h? So what's 2 plus
Why
h
does that
squared?
just be like h over h?
Well, let's do it carefully. What's 2 plus h squared? We use FOIL, okay?
Yeah.
It's 2 times 2 plus 2h plus h squared, or 4 plus 2h plus h squared,
Yeah.
okay? When we have x squared minus 4, what does that, what we put in x equals 2 plus h, what does x squared plus 4 become?
X squared.
Minus 4. If x equals 2 plus h,
X equals 2 plus 8.
yeah, 2 plus h.
So that'd be 4 plus 2h plus h squared minus 4.
Wait, I went the wrong way. So we just put in 2 plus h for x, right?
Yeah.
And the bottom we put in 2 plus h. Now we use FOIL to expand the top.
Cancel the
Yeah. So what can we cancel the
2h
top?
plus, well, I was saying what you would keep, but
Okay.
you'd cancel the 4, negative 4, and on
Cancel-
the bottom 2, negative 2.
Right. So we cancel that, and it's just 2h plus h squared over h.
Yeah.
Well, what's 2h divided by h?
H. 1h.
2h divided by h.
What does that just be? So 2h divided by 8. So it'd be like 2 divided by 2. No, it'd be like 4 divided by 2, which would just be 2. So wouldn't it just be h?
Well, we have, what would h divided by h be?
1.
So what would 2h divided by h be?
2.
2. What would 3h divided by h be?
Oh yeah, right, 3.
3. So if you have 2h divided by h, that's just 2. What about h squared divided by h? What would that be? That would be h. So the 2h plus h squared over h is just 2 plus h.
Yeah.
And as h goes to 0, what does 2 plus h look like?
2.
2. So does that make sense?
Yeah.
So we've just shown that this limit is equal to 2. I'm going to show you an easy way to cut that. Remember how we earlier did, like x minus y times x plus y?
Mm.
And we saw that that was x squared minus y squared. If I have x squared minus 4, I can write that as x minus 2 times x plus 2.
Yeah.
And so the limit as x goes to 2 of x squared minus 4 over x minus 2 is just x minus 2 over times x plus 2 over x minus 2. And then we just cancel the x minus 2's.
Yeah.
And then we have just the limit as x goes to 2 of x plus 2, and that's just going to be 4.
Yeah.
So not all limits are easy to compute. in an earlier coronavirus lecture, the first one, we actually got these formulas for pi, and these formulas only involve 2 and radicals of 2 and radicals of, and so on and so on. And so when you look at this, it's not easy to see what is this limit equal to. This is going to pi. All right. We're now ready to move on to calculus. So we're going to move on to calculus for a little bit, and then we'll stop. So we're going to talk about average speed. So it's often a good idea to add units to a problem to tell a story. So for example, if I have the curve y equals f of x, maybe x represents time and f of x represents distance. So we might be plotting.
Wait, x represents time or
yeah,
y?
so x represents time.
Oh.
And then f of x will tell us where you are at a given moment in time.
Okay.
Typically, what time do you start your trip?
At 0?
Yeah, typically it's easy to start things at 0, but you don't have to. What might be a better variable name to use for time rather than
T.
x? Yeah, a lot of times you would use f of t.
Yeah.
But we often like to use y for the output.
Yeah. In my math class, we would use d.
Yeah, I can see that. So let's let f of 0 equal 0. So we start at home. And let's say we end the trip at time 2. And we'll say, oops, that should have been f of 2 equals 110. So at time 2, we're 110 units from home. What is our average speed? What is our fastest speed? Our slowest speed? Our most common speed? Which of these questions can you answer?
Or average?
So if we start at 0 and we end 110 miles away at 2 hours, what was our average speed?
55 miles.
55 miles. We look at the distance traveled, 110, divided by the amount of time. Okay. What was our fastest speed? Yeah, no idea. Maybe we were going up to 200 miles per hour in one small section. Maybe
For like 30 seconds.
For like 30 seconds. What was our slowest speed? I don't know.
We're probably 0.
Probably 0 at the end of the trip or at the start of the trip, but maybe not. Maybe we just kept driving.
Yeah.
What was our most common speed? Yeah, we don't know. Really, the only question we can answer is the average speed. And as was remarked, it's 110 over 2.
Which is 55.
Which is 55. So we should have units. Maybe time is in hours, distance is in miles. So the average speed is 55 miles per hour. So computing average speed is not that bad. And this should remind you of some stuff you're doing in algebra. We look at, say, going from time A to time B. At time A, we are f of A units from home. At time B, we're f of B units from home. And so the average speed is the change in distance divided by the change in time. So this is going to give us a straight line connecting them. This is the change in distance. This is the change in time. What does this remind you of?
Slope intercept.
Yeah, it reminds you a lot of slope. So all the stuff you're doing in Algebra 1 is useful.
Apparently.
So let's say we take a linear function, cx plus d. So maybe for definiteness, maybe take 3x plus 5. And so here, I believe it's a plot of 3x plus 5. Okay. Let's compute the average speed from A to B. And my claim is that, do you think that for a linear function, that your average speed is constant?
Yeah.
Yeah, because if you look at what's going on over here, we're drawing a line connecting those 2 points.
What's the red line?
The red line is your curve y equals f of x. So I tried to just draw some kind of strange curve. And I tried to have it so that f of x was always increasing, that we're not going in reverse as we drive on the highway. So let's calculate the change in distance, f of b minus f of a. Well, what would f of b be?
F of x, right?
So f of x is 3x plus 5. What would f of b equal?
3b plus 5.
3b plus 5. What would f of a be?
3a plus 5.
And now when we want to group them, we have 3b plus 5 minus 3a minus 5. The 5 and the minus 5 cancel, and we have 3b minus 3. The change in time is just b minus a.
Yeah.
So the average speed from A to B is the change in distance, 3b minus 3a over b minus a.
Change in y over change in x.
Change in y over change in x. We factor out 3 and we get 3b minus a over b minus a. And what's b minus a divided by b minus a?
3. Oh, 1.
1. So we just get 3. So the speed, it doesn't matter when you start or when you stop, your average speed is always 3 for a line. So in that sense, the line is kind of boring. It's like you've set cruise control and your car is going at a constant speed. Now, if we do a quadratic, it's a little bit more interesting. So this is a degree 2. Let's say we have x squared plus 3x plus 1. So what this means is as time passes, you're really getting further and further away from home. And so we want to calculate the average speed from A to B. So what's the change in distance? We plug in x equals b, we would get what?
Wait, well,
If you want to calculate the change in distance, so we
b
go
squared plus
b squared,
3b plus 1.
and then we subtract off f of a squared plus 3a plus 1. So the 1 and the 1 over here will cancel, and we'll get b squared plus 3b minus a squared minus 3a. So we group things together. We group the b squared minus a squared together, and we group the 3b minus 3a together. And the b squared minus a squared, oh wow, we keep seeing this again and again.
B minus a.
Times b plus a. And this is going to just be 3 times b minus a. So we can pull out the b minus a. It's going to be b minus a times b plus a plus 3. The change in time is just b minus a. So the average speed is the change in distance over the change in time. What cancels from the top and the bottom?
B minus a.
B minus a. We're left with b plus a plus 3. So this is now more interesting. The average speed depends on when you start and when you end. Okay. So, you know, the change in distance, whoops. Okay. So we grouped it together. What happens in the limit as b goes to a? So as b gets closer and closer to a, what does b plus a plus 3 go to? As b gets closer and closer, as b gets closer and closer to a.
It goes to like a squared plus b.
Why
plus
a squared?
3. Well, like, oh wait, no, 2a.
2a.
My bad.
2a. Yep, that's right.
Okay, yes.
Yep. So it goes to 2a plus 3. And okay, so I agree that as b goes to a, this goes to 2a plus 3. What quantity does this represent? So you're calculating the average speed from a to b, where b is getting closer and closer and closer to a. What do you think this represents?
Driving to someplace.
But you need to give me some kind of interpretation.
Like
What kind of speed is it? It's no longer the average speed.
The speed limit.
Not the speed limit.
The fastest.
Not your fastest speed. So let's think.
The speed you go the most.
Not the speed you go
Your
the most.
slowest.
No. So think. Average speed is the time.
Oh, the how much time left till your destination?
Nope. You're looking at, we start off at A and then we go to B. But as B gets closer and closer and closer to A, what do you think your average speed is getting closer and closer to representing?
The actual time.
Not the actual time, the actual what?
Speed?
The speed. How do you think a car calculates the speed it's traveling?
I don't know. It sees how far it is, like a minute.
Yeah. So the way that, well, but a minute, is a minute a good amount of time for a car? Because a lot can happen in a minute.
Like an hour?
An hour? If the car wants to give you the instantaneous speed,
A couple seconds?
maybe not even a whole second, maybe a tenth of a second.
Yeah.
And you see how much the wheel has turned in a tenth of a second. So the average speed over shorter and shorter intervals should approximate the instantaneous speed at A.
Yeah.
So that's what's going on here. That if we take the limit as B goes to A, this should convert to your instantaneous speed. And that's what we're going to compute now. So the instantaneous speed is 2A plus 3. So what I did now is I took a function x squared plus 3x plus 1, and I calculated, let's say x equals 1, and let's choose different values of b. I chose b to be 2, 1.9, 1.8, 1.7, all the way down to 1.0. I looked at what is f of b. Okay. I looked at the change in distance. I looked at the change in time. And I looked at the average speed from 1 to b. And when we go from 1 to 2, the average speed is 6. From 1 to 1.9, the average speed was 1.9.
Yeah.
5.9, 5.8, 5.1. And now, wait, something's going wrong when I take b equals 1. Why do you think it might be hard to find the average speed from 1 to 1?
Because you're divided by 0.
Yeah, what's the change in distance?
0.
And what's the change in time?
0.
0. Now, the blue line is the actual function. It's the actual quadratic.
Yeah.
This line over here is the line that goes through the same point on the curve, but has the slope of the speed 1.5.
Yeah.
Does that look like a pretty good fit to your curve?
Yeah.
Yeah, that straight line is a really good approximation.
Except it has like a negative.
Well, but I'm
The
saying,
very beginning.
but here's the thing, if you
I guess, which makes sense because you're backing out of your driveway.
well, if you imagine you're traveling from Boston to New York,
Yeah.
do you think there are times when you're traveling quickly?
Yeah.
Yeah. Do you think there are times when you're traveling slowly?
Yeah.
Yeah, maybe you're getting stuck in traffic or at a light. And
Probably
so,
not going to hit lights
true.
on that. You're probably
Well-
just going to take 95.
Or maybe when you're driving on the highway, all of a sudden there's a car in front of you that's not traveling quickly, so
Then
you
you
have to slow
pass them.
down. Well, but you might have some trouble passing them at first. But here's the thing: if you look down at the speedometer and you see you're traveling at 55 miles per hour,
Yeah.
do you think you're still traveling around 55 miles an hour a tenth of a second later?
Yeah.
Is that enough time for the car speed to really change that much?
No.
Probably not. And that's why for small amounts of time, the instantaneous speed and the average speed, they're going to give wonderful approximations. So the instantaneous speed at x equals a is just the limit as b goes to a of f of b minus f of a over b minus a.
Yeah.
So we can write b goes to a as we can write b as a plus h with h going to 0. So what's a plus h minus a?
A plus H minus A.
Yeah.
A plus. Wouldn't that just be H?
It would just be h.
Yeah.
And so,
Yeah.
so what we're doing is we're calculating the average speed over smaller and smaller intervals.
Yeah.
And we're taking the limit as the interval goes to 0. This is calculus.
Yeah.
This is, depending on where you are, 10th, 11th, or 12th grade, or maybe freshman year in college. So if h was 0, we would have 0 over 0, which we can't do, but h is never 0.
Yeah.
So we need a name for the new function to denote speed. And do you know why we call it f prime? So the prime means derivative. And we use this because we're trying to say, look, it's related to the original function f. That's why we're going to call it f prime.
Yeah.
So let's do an example. Let's take the straight function 3x plus 5.
Yeah.
Okay? And let's calculate the instantaneous speed at x equals a.
Yeah.
So what would we have? Well, the instantaneous speed at a is the average speed as h goes to 0.
Yeah.
So it's the change in distance over the change in time.
Yeah.
So if I plug in a plus h, I get 3 times a plus h plus 5 minus 3a plus 5.
Yeah.
How would you multiply out 3a plus h plus 5?
3. Why do you do like inside outside?
So you tell me, what do I get when I multiply 3a plus h plus 5?
So 3A plus 3H plus 5.
Good. So you have 3a plus 3h plus 5 minus 3a plus 5 all over h. What cancels in the top?
Oh, 3A plus 5.
And so we're left with just the limit as h
Which
goes to
means
0
3.
of 3h over h.
Which is just 3.
Yeah, because h over h, the h's cancel. It's the limit of 3 as h goes to 0. And that's just 3 because there's no h dependence. So we've just shown for any a, if f of x equals 3x plus 5, then the instantaneous speed at, that should be at a, is 3. So we often use the same variable for f and f prime to write f prime of x equals 3. So where do you think the 3 is coming from? Why do you think the speed is always 3 if the function is 3x plus 5? Where do you think that 3 is coming
That's
from?
3X.
Yeah, it's coming from the 3 and 3x.
So like my feeling is if we change it to 5X, it would become 5.
I think that's a great thing to check. And so the coefficient is coming from the linear term. So if we now said, what if we had cx plus d, then all that changes is then we have c x plus h plus d minus cx plus d. So it's cx plus ch plus d.
And the CX plus D cancels.
And you're left with ch over h. What's the limit of ch over h? It's just c.
Shot.
And what is the limit as h goes to 0 of c?
C.
C. So if f of x is cx plus d, then f prime of x equals c.
Yeah.
So we've now done linear functions. We now know how to calculate their speed. What should we do after doing linear functions?
Non-linear function? I don't know.
So what's the next one to do? This is ax plus b or cx plus d. It's a degree 1 function. What should we look at next?
A degree 2?
A degree 2.
Would that be like with the square?
Yeah, so let's look at a quadratic. And this is the one we're going to need for Newton's method. Okay? So we have 3x squared plus 5x plus 2. So we want to calculate. So because this is a little bit more involved, let's do it slowly. What would f of x plus h be?
F of x plus h?
Yeah. If f of x is 3x squared plus 5x plus 2, what happens when we put an x plus h? Just do it very slowly.
F plus h?
You have f of x plus h. So f of input is 3 times input squared plus 5 times
So
input plus 2.
it'd be 3x plus h squared
3x plus h squared.
plus 5x plus h squared. I mean, just x plus h plus 2.
Plus 2. Perfect. And now, how do we expand out x plus h squared? We use,
Inside x.
first,
FOIL.
outside, inside, last, we use FOIL. Or we could use Pascal's Triangle, which is why we proved it.
Yeah.
So it would be 1x squared plus 2hx plus h squared. How do we expand x plus h? We just use Pascal's Triangle, just there's nothing to do. So f of x plus h is 3x squared plus 6hx plus 3h squared plus 5x plus 5h plus 2. It's a little bit more involved than what we had for the linear. F of x is just 3x squared plus 5x plus 2. So if we look at their difference, what's the change in distance? The 3x squareds cancel, the 5x's cancel, the 2's cancel. We have 6hx plus 3h squared plus 5h. So that's the top. What's the denominator?
H.
So that's not so bad. So we divide this change by h. What's 6hx over h?
6x.
6x. H is cancelled. What's 3h squared over h?
3h.
3h. What's 5h over h?
5.
5. And now we want to look at what is the limit as h goes to 0. As h goes to 0, what does 6x go to?
6x.
6x. What does 3h go to?
0.
0. What does 5 go to?
5.
You get 6x plus 5. So what we've now shown is that the speed actually depends on where you are. So if the function, if our distance is 3x squared plus 5x plus 2, here's the hard part. The speed is 6x plus 5. Where do you think the 5 came from?
Yeah. Plus 4. The 5h.
The 5,
Wait, h?
not 5, well, yeah, 5h, but in the function f of x is 3x squared plus 5x plus 2.
5x.
Yeah, it's coming from the 5x. How do you think I got 6x from this? What do you think the 6x?
Squared.
Yeah, how do you think the 3x squared gave me the 6x?
You have 3x plus another 3x, which would be 6x.
But why are we getting, okay, so are you saying it's like 3 times 2?
Yeah.
So if I had 4x squared, what do you think this would become?
8.
8x. And notice how the power x here is 1 less than the power here?
Yeah.
And the power x here is 1 less than the power there.
Yeah.
And so it is coming from, as you said, these coefficients. And so if we give you a quadratic, we get that f prime is equal to 2ax plus b. So we see f of x is ax plus b.
Yeah.
For linear, then f prime of x is just a. What would you guess for ax cubed plus bx squared plus cx plus d? So here we guessed it was 2 times a, x to a 1 less power, b times 1 times x to a 1 less power.
So a times 3.
A times 3, and what power of x?
X squared.
X squared.
B times 2.
B times 2, x.
C.
Yeah. And you are correct. The answer is 3ax squared plus 2bx plus c. So we need to calculate, good job, x plus h to the n. So say we're just looking at the function ax to the n. Okay? So we believe it should be n8 x to the n minus 1. What would we use to expand out x plus h to the n?
Oil.
could use FOIL, but let's say I tell you n equals 7. How could we quickly expand out x plus h to the 7?
Pascal.
Pascal's triangle. So we would just use Pascal. All right, so why do we care? So we're almost done, and then we're going to do the rest of this tomorrow. We can use the instantaneous speed to approximate the function. So you've talked about how you've plotted lines in class, and you do like point slope or point point.
Yeah.
So we showed if f of x is 3x squared plus 5x plus 2, then f prime is 6x plus 5. So this is the instantaneous speed.
Yeah.
So consider the point x equals 2.
Yeah.
So when you put in 2, do you agree that f of 2 would be 12 plus 10 plus 2?
Yeah.
3 times 2 squared plus 5 times 2 plus 2.
Yeah.
What's the instantaneous speed when x equals 2? What's f prime of 2?
12.
12
5.
plus 5 is 17. So now we draw the tangent line at this point using the slope. So I want to go through this point on the curve, the point 2f of 2, or the point 224, and I want the slope to be the f prime, the derivative at 2, or negative 17, or positive 17. And so we get the equation of a line is y minus the y value is the slope times the x minus the x value. Have you seen this before?
Oh. Is that just slope intercept?
No, because I don't know the intercept. This is called point slope. You know a point on the line and you know the slope.
Oh, yeah.
And then when we expand it out, we get y equals 17x minus 10. At that point, now it's in point slope form. But it's easier if I know the point and the slope. I just say y minus 24 is 17x minus 2.
Yeah.
So are you surprised that the tangent line is a good approximation near x equals 2? Not really, because your speed can't change by that much over a short period of time. So if you make the assumption that your speed is always constant, is there going to be a big change? No. All right. So we will stop here and do the rest tomorrow. So tomorrow we will do part 4, divide and conquer versus Newton's methods and practice. Hope you enjoyed today's lecture.